Good morning, children. So, in today's class, we are going to start the gaseous state. In previous class, we have seen different types of forces, that London forces, in that dipole forces, dipole induced forces, and about thermal energy. So, in today's session, we are going to learn something about gaseous state. So, in a periodic table, if we see about 118 elements, among 118 elements, only 11 elements exist as gases under normal conditions. So, the atmosphere where we live is nothing but troposphere. For human being to survive, we require a gas, that is nothing but oxygen. So, gaseous things means, or a gas plays a vital role in our life, isn't it? So here, if we see, some laws were discovered. The gas laws were discovered as a result of their experimental studies. So to lay a laws for the gases, we have to do some experiment. Basing on experiment studies only, we can give some gas laws. So these laws show some relationship between measurable properties of gases such as mass, volume, pressure and temperature. What I said, gas laws were discovered as a result of their experimental studies. So these laws shows the relationship between measurable properties of gases such as mass, volume, pressure and temperature. So before moving into the gaseous laws, some gaseous laws, we will see some of the properties of gases. So we already know the force of interaction between their molecules are negligible. So what do you mean by that? The intermolecular force of attraction between the particles of the gases is very less. That is why they can easily flow, isn't it? And the space between them will be very large. So that is why the gas molecules can move freely. And next, gases are highly compressible. When you take a balloon, if you press the balloon, what happens? It can be compressed easily, because whatever pressure exerted by this gas, they can be equally distributed in all directions. So gases are highly compressible. Next, volume and shape are not fixed. So here, if you take any bottle, empty bottle, yes, so here how much volume it can be filled, that much volume only will be there for that gas. And what the shape it can occupy the shape of the bottle. If we take an example for a room, in a room how much gas it can be there, yes, so how much gas it will be there, some amount, isn't it, or some liters you can say. And what is the shape of the room only it can take. So volume and shape are not fixed, it will be changed by changing the containers, or by changing the rooms, or by changing the shapes basing on which they are present. Next, gases exert pressure equally in all directions. For example, take this one bottle or any square shaped container. If you fill with some gas, say O2 or anything, what happens? All the gas particles will move in all directions. They exert pressure in all directions. So this direction, forward and backward directions, it will be equal. So no one particle will be show any one pressure, but all the particles whatever present in a gas, they show equally some pressure in all directions. And so children, one gas will be taking rest, another gas will be in motion. It's not like that. All gases show some motion and they will exert some pressure in all the directions. Next, gases have much lower density than solids and liquids. So what do you mean by density, children? Density is nothing but mass by volume. So here, when we compare with the liquids or solid, they will be having solids having rigid shape. So basing on that, they will be having some particular mass and volume, right? And liquids also, it can be measurable, whether in liters, okay, like that. But whereas gases, if we see, when we compare among with these three, gaseous, solids and liquids, gases will be having very low density. Next, gases mix evenly and completely without any mechanical aid. So for example, here I am taking any spray perfume. If you spray perfume in your room, that whole room will be occupied that this fragrance, isn't it? So gases mix evenly and completely without any mechanical aid. We don't require anything to mix with the air. Okay, that perfume do not require any particular mechanical aid to mix with this air. So here I have taken example O2 and H2. When we put both this in a container, they both will be mixed. Okay, so what are the gaseous laws are there in this lesson? We are going to see each and everything one by one. First one is Boyle's law. Okay, what a Boyle's law states that. So look at here, Boyle's law states that at constant temperature, the pressure of a fixed amount of gas varies inversely with its volume, or simply at constant temperature, the volume of a given mass of a gas is inversely proportional to its pressure. That means, P is inversely proportional to its volume. They said this one. So how? So look at here, I have taken a gas in a container, okay, and here piston is present. So when we move the piston upside, what happened? The volume increases, isn't it? And the pressure decreases. So when you push this piston inside towards down, what happens? The volume decreases. The pressure, what happens to the pressure? Pressure is increasing. When you apply some amount of pressure, the volume of a gas is going to be decreased. So that is the statement given by Boyle's law. At constant temperature, the volume of a given mass of a gas is inversely proportional to its pressure. That means when pressure increases, volume decreases. When pressure decreases, volume increases. By this diagram you can understand. So that means P is directly proportional to, or P is inversely proportional to 1 by V. So if you want to remove this proportionality constant, PV equal to constant, you can write like this. So at constant temperature, if we take two types of pressures or two types of volumes, then P1 V1 equal to P2 V2. Understood, children? P1 V1 equal to P2 V2. So if we draw a graph, okay, if we plot a graph like this, on x-axis we are taking volume of a gas and y-axis we are taking the pressure of a gas. So what I said, when pressure increases, volume decreases. When pressure increases, volume decreases, isn't it? So here this shows that pressure is inversely proportional to its volume. When pressure is high, volume will be decreasing. And next, if we plot another graph where pressure is on y-axis and 1 by volume on x-axis. So what happens here? It gives a straight line. Okay, it gives a straight line. So what it indicates? So here a graph of pressure versus reciprocal of the volume, that is 1 by V volume. The curve is a straight line indicating regular increase in 1 by V with increase in pressure. Regular increasing in 1 by V with increasing in pressure. So understand here. So now look at this graph. So graph 1, each curve corresponding to a different constant temperature. At different temperatures we are taking, and it is known as isotherm. So a graph obtained by plotting pressure of a gas against its volume, and it is called an isotherm, and it is plotted at constant temperature. So iso means same, therm means temperature. That means a constant temperature, same or constant temperature. So here whatever each curve we are giving, each curve you have drawn here, each curve corresponds to a different constant temperature and it is known as isotherm. So what do you mean by that? At constant temperature only we are drawing this graphs, we are plotting these graphs. So by Boyle's law, what did you conclude? We have concluded that gases are highly compressible. Gases are highly compressible. That means density is directly proportional to its pressure. When density increases, pressure increases. When density decreases, pressure decreases. So basing on this one question I have written, see, a vessel of 120 ml capacity contains a certain amount of gas at 35 degrees centigrade and 1.2 bar. Bar means pressure. Okay, so the gas is transferred to the another vessel of volume 180 ml at 35 degrees centigrade. So here temperature is constant, Yes, and volume is different. Volumes are different. At one pressure is given, what would be its pressure? So whatever things we got V1, T1. Here T2, V2 you have to find. So look at here, V1 is 120 ml, P1 is 1.2 bar, V2 is 180 ml, P2 you have to find. So from the Boyle's law, P1 V1 equal to P2 V2. So what you have to find? P2 you have to find. Pick it out outside, this P2 outside, and this V2 will be going down. So P1 V1 by V2. So P1 how much? 1.2. V1 how much? 120. And V2 how much? 180. So cancel each other. This 0 0 will be get cancelled. 6 3s are 6 2s are 3 1s are 3, 0.4. So what is the pressure we got? We got 0.8 bar pressure. 0.8 bar pressure. So this is how you have to find the pressure or volume. Anything, any three things they will give, one of the thing you have to find. So this is about Boyle's law. What do you mean by Boyle's law, children? At constant temperature, the pressure of a fixed amount of a gas is inversely proportional to its volume, or the pressure of a gas is inversely proportional to its volume. Next comes to Charles' law. Next one is Charles' law. So here at a constant pressure, the volume of a given mass of a gas is directly proportional to its temperature. So what he has said, at a constant pressure should be at a constant, the volume of a given mass of a gas is directly proportional to its temperature. That means V is directly proportional to temperature. Remove this proportionality constant, then we will get V equal to KT. V by T equal to K, where K is the constant. So from this you can get V1 T1 equal to V1 by T1 equal to V2 by T2, or you can write V1 by V2 equal to T1 by T2. So how you can know this? So here see, I had taken a small apparatus which consists of a volume, some water liquid is present, this is thermometer, this is scale, and this is an capillary tube. Okay, down Bunsen burner is there. So and this capillary tube is sticked with the help of a rubber band. Okay, before here we can see some gap, it is filled with some gas. So when you put on this Bunsen burner, what happened? The temperature will be increased. That can be noted in this thermometer. When temperature increases, okay, when temperature increases, the volume which is occupied inside this capillary tube, that means it will be like this. So before it is up to here, no, it will be up to here. So what did you understand here? So when temperature is increasing, the volume in the capillary tube also increasing, making this this water will be constant, means it will be same. So basing on this, if you plot a graph, take volume on y-axis, temperature on x-axis. So this is minus 273.15 Kelvin, and these are the pressures, this P1, P2, P3, P4. So each line of the volume versus temperature graph is an isobar. Isobar is nothing but, iso means constant, bar means pressure, at constant pressure. So the lowest hypothetical or imaginary, this one, see, look at here, this dotted lines, the lowest hypothetical or imaginary temperature at which the gases are supposed to be occupy the zero volume is called absolute zero. So what do you mean by absolute zero, children? The temperature at which all motions, okay, all the gas particle motions will be stopped, means ceased, that means it will be stopped, is called absolute zero. The one, what we can say, so here this can be, so here look at here, here the temperature, another diagram with this another diagram. So look at here, volume is directly proportional to temperature, I said, isn't it? When volume increases, when temperature increases, volume also increases. So this is volume. So behind this, the volume where it becomes zero, that means no gas will be occupied, where the gas will becomes zero, that point is called 0 Kelvin, or So this point where 273 degrees Celsius is called 0 Kelvin. This is 0. Okay, 0 Kelvin, where the motion of the gas particles becomes 0. That point is called absolute 0, the lowest hypothetical or imaginary temperature at which gases are supposed to be occupy the 0 volume. When there is 0 volume, we cannot find anything. So that is called absolute 0. That absolute 0 value will be minus 273.15 degrees Celsius. Okay, so to become easily to when the calculations and all, to make it easy, the scale is called absolute scale or thermodynamic scale or Kelvin scale, where the value of 0 degree centigrade equal to 273 Kelvin. This 1.5, sorry, this 0.15 you can write or no problem. Okay, 0 degree Celsius equal to, where 0 degree Celsius, where the Kelvin scale start, that is 273 Kelvin. So basing on this, one example I have written. On a ship sailing in specific ocean where temperature is 23.4 degrees Celsius, a balloon is filled with 2 liters of air. So what will be the volume of the balloon when the ship reaches Indian Ocean where the temperature is 26.1 degrees centigrade? So what are the things we got? We got volume. Okay, V1 we got and T1 we got. Yes, next temperature T2 we got. So what we have to find? We have to find the volume of a balloon at Indian Ocean, isn't it? So what is the formula, children, from Charles' law? V1 by T1 equal to V2 by T2. Put all the things in this. So V2 equal to, we want V2, no? So V2 equal to V1 T2 by T1 equal to 2 into, so here it is given in degree Celsius. So you have to convert in Kelvin square. So how you will convert? You have to add. Okay. So for 0 degree Celsius equal to 273 I said. Then 23.4 degrees Celsius, to convert in Kelvin scale, what you will do? You have to add. You have to add. See, 23.4 degrees Celsius plus 273 equal to 296.4 Kelvin, and T2 where 26.1 degrees Celsius, okay, to convert in Kelvin scale, plus 273. You have to add plus 273. Then you will get 299.1 Kelvin. So keep all those things here. 2 into 299.1 by 296.4. Then 2.018 liters of volume. So we got V2 is this. Understood? So by the time when ship reaches the Indian Ocean, the balloon is filled with 2.018 liters of air. This is about the two laws, and another laws we are going to deal in the next class. Thank you, children.